Good evening, everyone, and welcome to this special lecture this evening. Fáilte roimh go léir go dtí an líocht speisialta an tróna seo. The Dublin Institute for Advanced Studies is hosting this lecture this evening as part of the programme for the Festival of History, and it is also part of our programme for the 80th anniversary of the Dublin Institute for Advanced Studies. We have a number of other events that will be happening in the coming months, so please do visit our website and look at the usual channels to register for further events. And you can also register to be on our mailing list. Before I introduce our very special speaker for this evening, I will also introduce my colleague, Professor Peter Gallagher. Peter, if you could just make yourself known there. And Peter will actually chair the session once Jocelyn has completed her lecture and will deal with the questions. So from there, I'd like to move to introducing our speaker. And we're absolutely delighted that Dame Jocelyn Burnell has agreed to give this lecture this evening on the subject of the past and future 100 years of astronomy. Jocelyn, who is obviously from, I think most of you will know, is from this island, has held a number of positions in UK institutions, most recently in Oxford. She is, of course, an astrophysicist, and she has served as president of the Royal Astronomical Society and as president of the Institute of Physics. She has had a stellar, if you pardon the pun, scientific career for 50 years and has contributed very significantly to astronomy and astrophysics. And indeed, she has done so from a very early age. In 1967, as a postgraduate student, she discovered pulsars, one of the most significant scientific discoveries of the century. She's been a recipient of many awards and honours, but I will just mention one, which was in 2018, that she was awarded the Special Breakthrough Prize in Fundamental Physics for her discovery of pulsars. And I would note that she very promptly donated that funding to fund women and underrepresented ethnic minorities and refugee students to become physics researchers. As the Registrar and CEO of the Dublin Institute for Advanced Studies, and my name is Eucharia Meehan, I should have said that at the beginning, I'm absolutely delighted that Jocelyn is going to give us this lecture this evening, and I think there is no one better placed to give us a reflection on the subject of the past and future 100 years of astronomy. So without further ado, I will hand you over to Jocelyn. Thank you again, Jocelyn.
Thank you very much. Thank you, Eucharia, for that generous introduction. And thank you for the opportunity to be part of this historic year, historic in so many dimensions. I'm going to talk a bit about what we knew in astronomy about 100 years ago and what might happen in the next 100 years. The latter is always a little bit risky. I'm sure I'll be proved wrong very, very quickly, but I'll try. Right, and I should be able to move down a slide, but I can't. Good. So 100 years ago, 1920, what did we know? I'm having trouble moving down a slide. Yeah, thanks very much. So I want to mention the big optical telescope that the Earl of Ross, Lord Ross, built at Birr Castle. It was finished in 1845, just in time for the potato famine. But it was a superb telescope, and he used it to look at some of the nebulae, which were nebulous, vague things in our galaxy. And he made a drawing of one of them. It's called M51. Interesting spiral structure. Although they didn't fully follow the argument through at the time, what in fact they were looking at was not a nebulosity in our own galaxy, but another galaxy far, far away, seen through the outskirts of our galaxy. Let me do the next slide, please. So these two photographs show a Hubble telescope picture of M51 on the left and the Birr telescope 1845 image on the right. And it's a remarkably good image for 1845. It captures a lot of what you can also see in the Hubble image. And the next slide, please. So carrying on then from what we knew about in 1920, there had been this hint of nebulous things in our galaxy, which were very important, but weren't in our galaxy, but were a bit nebulous. And the next slide. So 100 years ago, in 1920, we knew that the Milky Way, our Milky Way, was a galaxy. We had a good idea of its size, how many stars it had in it, how much it weighed. But we hadn't yet appreciated that those nebulae, like the one I was just showing you, were actually other external galaxies. And that didn't happen till 1924, so less than 100 years ago, when the US astronomer showed that those nebulae were galaxies way beyond ours. And he introduced this subject with the lovely phrase, "We are not alone. There are other galaxies besides ours." And the next ones, please. So what is a galaxy? Well, we live in one. It's called the Milky Way. If this image was of the Milky Way, it isn't, because we can't get outside it to get that kind of picture, but if we were outside it and could photograph it, it would probably look something like this. And the sun and its planets are about 2/3 of the way out from the center. We're not at the hub of anything. We have a suburban address. The next slide, please. Our sun is one of a mere 100,000 million stars making up the Milky Way. It's a bog standard star. There's absolutely nothing special about it to the astronomer. And we also now know that the galaxy is disc-shaped, about 100,000 light years across, and it's spinning. So the sun is moving and the planets with it at about 200 kilometers per second. But we're not aware of that motion. We don't sense it. We're going in the direction of the constellation Cygnus. And the next one, please. Now, we now know of lots and lots and lots of galaxies. Perhaps the next most famous one is the Andromeda Galaxy, which you see in the left-hand panel. It's one of our nearest companions, the nearest probably. And again, it's a fairly typical spiral galaxy. What we've also discovered in the last 100 years is that galaxies themselves are not in isolations. Galaxies group into clusters of galaxies. We're in a cluster of galaxies called, very enterprisingly, the local cluster. Typical clusters of galaxies have hundreds of galaxies in them. And in the right-hand image, you can see part of a cluster of galaxies. And almost every patch of light and dot in that image is a galaxy, each with hundreds of thousands of millions of stars. Some bigger than our galaxy, some smaller, I dare say. Thank you. And the next slide. So we came to appreciate almost 100 years ago that the nebulae in our galaxy were actually other galaxies, and that they are large distance groups of stars, a bit like our Milky Way. We've also learned that galaxies themselves cluster, and we've also learned that besides the stars in a galaxy, there's gas and dust in the galaxy, and some of that gas and dust is made up of, well, all of it actually is made up of molecules. So there are clouds of, for instance, carbon monoxide in a typical galaxy, and also clouds of water. It's dripping wet up there as well. And the next slide, please. I love this image. It's a black and white one, and you'd think it would be rather boring, but I think it's very stylish. It shows some bright stars and a cloud of this kind of dust, and the top tip of the cloud is being warmed up by the starlight and is glowing or it maybe possibly is reflected light. There's a lot of that dark material. Some of it is dust, some of it is simple molecules. So there's chemistry in space as well. In fact, very intriguing chemistry. Space is so empty, it's hard to see how atoms get together to make molecules, but clearly they do. And the next slide, please. Also, in the last 100 years, we've discovered black holes, masses in our galaxy, masses that do not emit any light, but of course have gravity. And we've also learned that in the centers of many galaxies, there are huge black holes. And I'll say a bit more shortly about the black hole at the center of our galaxy. It's much, much bigger than the black hole associated with individual stars, formed from individual stars. It's really huge. And the next slide, please. Also, 100 years ago, we didn't know about the formation of our universe and its subsequent evolution. I think we tacitly assumed that everything had always been much the same as it was, as we saw it now. But in fact, we now know that our universe had a beginning. About 14 billion years ago, there was a very sudden expansion out of a small spot. We colloquially call it the Big Bang, and our universe has been expanding ever since. 100 years ago, we didn't know about the age of the universe, 14 billion years, nor did we know about the scale of the universe, how much it has expanded in those 14 billion years. One of the useful things we've discovered in the last 100 years is called the cosmic microwave background. This is a very low-level radiation. It's basically some of the heat energy left over from that initial explosion from the Big Bang 14 billion years ago. And the next slide, please. So I'll say a bit more about what we found in the last 100 years. Move on to the next slide, please. So one of the things that maybe you don't immediately think of as being astronomy is the discovery of cosmic rays. The timing of this doesn't fit too well with my 100-year threshold. He actually discovered cosmic rays before 1920, but he didn't get the Nobel Prize till after 1920. So I'm putting the discovery of cosmic rays by Victor Hess into this talk. Physicists around that time knew that there was some kind of ionizing radiation because they could see their equipment changing with time as the radiation came through it. Things wouldn't hold a charge, for instance. And Victor Hess suspected we were getting a rain of charged particles from outer space. He could see some of these charged particles here on Earth, but he had to prove that it came from space. And very bravely, he went up in a high altitude balloon with his equipment. He went up to 17,500 foot without oxygen. And his equipment showed that as he went up, this radiation increased, which strongly implied it was coming down from outer space. This radiation was called cosmic rays. People were very, very skeptical, and I think that's partly why he didn't get the Nobel Prize for about another 20 years. But in the end, he did. And cosmic rays and the study of these particles from outer space is one of the branches of astrophysics these days. And the next slide, please. So cosmic rays, charged particles, often quite heavy charged particles. We're now also studying from outer space lighter particles, things like the neutrino, which is very elusive. This, of course, is nowhere on the main electromagnetic spectrum that includes light and radio waves and things. And we now do astronomy across the whole of the electromagnetic spectrum, all the way from long wave radio waves, long wave radio waves, through millimeter waves, through infrared, optical, ultraviolet, X-ray and gamma ray. So there's a whole new spectrum there as well. And next slide, please. So this shows the electromagnetic spectrum. It doesn't show you any of the particle stuff, and there's another whole spectrum I'll talk about later. But this has got the little optical bit that we see in the middle, the rainbow. That's the only bit of this whole spectrum that our eyes are sensitive to. If we go out the red end, we come to infrared, then millimeter waves, then radio waves. And if we go out the violet end, we come to ultraviolet and X-rays and gamma rays. And we now do astronomy across that whole spectrum, right to left of that whole spectrum. Don't always do it in the same way, but we do pick up all those radiations. And the next slide, please. So besides cosmic rays and astronomy in the electromagnetic spectrum, the other thing that's happened in the last 100 years is that we now have space flight, and we've been sending satellites up into space. And some of the most interesting ones have explored the solar system, Mars, Saturn, some of the asteroids, comets, things like that. So we've expanded in many dimensions in the last 100 years. The next slide. So space flight, exploration of the solar system. We've discovered a lot of, well, we have discovered Pluto in the last 100 years. We've discovered all the things out beyond Neptune in the last 100 years. And we're starting to find planets round other stars. So not just the sun has planets, but so do other stars up in the night sky. We call those planets exoplanets. And if you look up at the night sky on a dark, clear night, you should say to yourself, there's as many planets up there as there are stars, because there are a lot of exoplanets. And they come in all sorts of shapes and sizes and positions. The next slide, please. So in the last 100 years, we've learned about the constitution of stars, why they shine, what their energy source is, how they evolve. We've moved into high energy astrophysics, X-rays and gamma rays. We found gamma ray bursters. We found neutron stars or pulsars. More recently, we found gravitational radiation. And that's very exciting. It's a whole new spectrum. And it's turning up a lot of black holes of a mass range that we didn't know existed. Black holes that might be 20 or 30 times the mass of the sun. So we have come a long way in our 100 years. The next slide, please. This has been made possible because astronomers and physicists have had funding from our governments, from scientific foundations, from private individuals, and we've had a lot of support from industry. And there've been a lot of smart people, astrophysicists, space scientists, engineers, computer specialists. And between those all, we've developed a lot of brilliant technical innovations, which have been really necessary to help us study space in so many new ways. And the next slide, please. So some remarkable developments. I can't deal with everything, but I want to say a bit more about some of them. And I'm focusing mainly on things in the last 50 years. And the next slide, please. So radio astronomy has come about since the end of the Second World War. People who worked in radar during the Second World War, at the end of the war, took some of the radar receiving equipment, turned it towards the sky, and discovered that they were picking up radio waves from things up there in the sky. This radio telescope is the famous one at Jodrell Bank. It's just been made a World Heritage Site, so they've got to keep it standing, which will be an interesting problem for them. But it is a magnificent telescope, and it's very big and has contributed to many key discoveries. Next slide, please. We've used the rockets that Wernher von Braun developed to launch bombs on London, rockets on London. We've taken those Wernher von Braun rockets and we've made them bigger and more efficient, and we've used them to launch satellites up into space. This is necessary for subjects like X-ray astronomy because the Earth's atmosphere prevents X-rays from space reaching down onto the surface of the Earth. The atmosphere cuts them out, which is for our own good. But if you're an X-ray astronomer, you've got to get your equipment up above the Earth's atmosphere. Also, if you're a gamma ray astronomer, those are the main frequencies that use the satellites. They are of some use at other wavelengths. Thank you. The next slide, please. One of the satellites that was launched is called COBE. COBE studied the cosmic microwave background. I've already mentioned that the universe began with a big bang from a very, very small volume. And initially it was very hot. And that hot material expanded with everything else and thinned out. And so the radiation from it has also thinned out, but there is still some radiation left over from the Big Bang. If anybody else is old enough to remember television sets that you tuned by turning a knob, you may remember that in between stations you were getting some kind of hiss, background noise. A little bit of that hiss came from outer space and is radiation from stuff left over from that hot Big Bang. But today, the best way of studying that is to get a satellite up into space above the Earth's atmosphere. And COBE was the first one to do that really, really well. It studied this background radiation. It plotted a spectrum of it, and you can see the spectrum in the bottom right diagram. The dots are the data, and the curve are the line, the data you would expect if you're studying a warm body, not really hot, just a few degrees above absolute zero. But that's classic data, and it beautifully fits the theoretical curve. And that's one of the main milestones in our progress. And it confirmed our ideas about how the universe began with a Big Bang. And the next slide, please. Now, I hope this yeah, it's going to run. Good. Each of the bluey green dots that you see in this diagram is a star. And we're looking right towards the center of our galaxy. And it's a sequence over a whole lot of years. You can see the date up on the top right. It stopped in 2013. Here we go again. Starts in 1995. So it's 7 or 8 years worth of data. And we can see all these stars moving. Now, those of you who've taught physics or have learnt basic physics know that things normally move in straight lines unless something forces it to change from a straight line. There is not a single straight line in this diagram anywhere. Things are moving in all sorts of curves and hairpins. And that's because there is something at the position where there is that star shape, something with massive gravity that pulls the stars in orbit around it and prevents them from going straight on. And by studying the orbits of these stars, they've been able to establish that the thing you can't see, where that star shape is, must be a black hole, and it has a mass of about 4 million stars, 4 million typical stars. This is the black hole at the center of our galaxy. And these stars are stars that live near the center of our galaxy and orbit around that black hole. I expect every so often 1 or 2 of them will get pulled into the black hole, but for the moment they are orbiting very nicely and showing us how there is this massive black hole at the center of our galaxy. Thank you. And the next slide, please. So leaving black holes and galaxies, I want to talk a little bit about stars, and in particular about planets, because one of the other major surprising discoveries in astrophysics in the last 100 years is how many planets there are round stars out there in the sky. At the moment, we know of about 4,000 planets round stars in the sky. The number is growing fast. The next slide, please. There are two main ways that you can tell that a star has a planet. One is, as the planet goes round the star, it tugs at the star a little bit. And even though you can't see the planet, you might see the star juddering around just a little bit. You'd see it if you were observing its velocity. You'd see that rather better than actually seeing any change in its position, given how far away the star is. The other main way you'd know if a star had a planet is if every so often the star got a little bit dimmer. Dimmer because there's a planet passing in front of it and blocking some of its light. So if that dimming comes at regular intervals, you know you've got something going round regularly, like a planet. Next slide, please. This graph shows how the number of known exoplanets has grown over the years. It starts at about 1989 on the left, it goes up to 2020. And the different colors show the different ways they've been detected. And you see the massive rise in the number of known planets, starting about 8 years ago, around about 2012. This is largely due to what satellites we have up there. There are some very good ones up at the moment. And the planets that were discovered because they tugged their parent star around, those are the ones that give rise to the red bit of the bars. The green bit of the bars comes from planets passing in front of their parent star and temporarily dimming it. Well, we're getting better and better at detecting exoplanets. And so this graph is going to continue to rush up, I expect. It's, I'm sure, already out of date. It dates from the 22nd of April this year. So it's had another 5 or 6 months to grow. The next slide, please. So moving still on to yet another topic, I'm going to talk a little bit about the universe as a whole. There's a pie chart here. There's a yellow, dirty yellow sector, which I've labeled ordinary matter. There's a pink sector called dark matter, and a blue sector called dark energy. One of the disturbing things in recent years is that we've discovered that we actually know less and less. We have discovered that there has to be something called, which we have called dark matter. That's in the pink sector. Dark matter holds galaxies together and prevents them from flying apart. We've seen millions of galaxies. Virtually none of them are flying apart, but they're rotating so fast they ought to fly apart, but they aren't. So they must have more gravity in them than we know about, which means whatever gives that gravity doesn't shine, so we call it dark matter. And there is an awful lot of dark matter around. Another disturbing thing we have discovered is, okay, there was this Big Bang explosion 14 billion years ago. The universe has been expanding ever since, but presumably that expansion is gradually slowing. No, it ain't. That expansion is gradually getting faster. And there's no way that the Big Bang can be responsible for that. There must be some other sort of agent, says she vaguely, pushing the universe apart faster and faster. We don't know what this is. We've called it dark energy, and there's one hell of a lot of it. So all the stuff I've talked about so far, fits into that tiny little dark yellow, dirty yellow sector. And everything else is either dark matter or dark energy, and we don't know what either of those are. So although I've been claiming we made great progress over the last 100 years, another way of saying is we're going backwards, since we seem to know less and less. Next slide, please. I want to say just a little bit about astronomy in our culture. This is a complete change of tack. For any physicists looking in, that little diagram on the right is a photograph of a bit of pavement in Portugal. The Portuguese do a lot of lovely black and white pavement mosaics. This mosaic reminds me of the two-stream instability. So physicists, do you think two-stream instability inspired that bit of pavement? Well, maybe. That might be some culture and astronomy interacting. Could I have the next slide, please? Ancient people didn't have floodlights, spotlights, flashlights, electric lights, house lights, safety lights. They had very, very little light. And they were much, much more aware of the night sky. And this photograph is of the kind of thing that they might have experienced. The Milky Way, that band sloping up across the center of the picture, is our galaxy. It's looking in the plane of our galaxy, looking out towards the rim. Can I have the next slide, please? The ancients gave names to the Milky Way, and I've got some of the names here from my collection. I think they're rather charming. The Aboriginal, or one of the Australian Aboriginal tribes, described the Milky Way as the rainbow serpent. In Celtic, it's the Silver Street. In China, the Silver River. Cree Indian called it the Path of the Spirits. Ancient Hebrew called it River of Fire. And the inhabitants of the Kalahari Desert called it the Backbone of the Night. And the next slide, please. Korean called it Silver River Water. Maori in New Zealand called it the Long Fish. The Setswana in South Africa said it was the place where the lightning rests. In Siberia, it was called Silicon River. I don't know if the element silicon was named after it, but I can't think that they knew about silicon at the time they called the Milky Way Silicon River. In Sweden, it's the Winter Road. In many languages, it's things like the Winter Road or the Starry Road. And my favorite one is from Thailand, where they respect elephants. They know it as the Way of the White Elephant. And the next slide, please. Another thing that's happened, probably only in the last 10 years or so, is the growth of citizen science projects. This actually started in Oxford, where a graduate student, God bless him, had literally 1 million galaxies, or images of 1 million galaxies, and he had to classify them. And he worked flat out for a week. And then he met in the pub with his supervisor and said, during this week, I've done so many classifications. There's no way I can do 1 million in my 3-year PhD. So they downed a few more pints and then realized they could put the images up on the web and invite the public, given a short tutorial, to help classify these galaxies. Are they elliptical? Are they spiral? And they did that. Chris Lintott was the supervisor. You may know the name. He is one of the people that does Sky at Night. And he went on the radio and television and told people about this, and the computer had a meltdown, but they got it sorted. And a lot of people have helped classify galaxies and done it very well. And now the citizen science theme has been expanded to a lot more astronomy and a lot of other projects as well. You can find the astronomy ones on the Zooniverse website, which is given at the bottom of this page. For instance, there's one to do with identifying small craters on the moon. There's another to do with watching the sun or solar storms coming up. Lots of different projects there. And the next slide, please. So even more risky, looking ahead in the future. Next slide, please. We're getting a number of big new telescopes. The one on the left, called the Vera Rubin telescope, the first big telescope to be named after a female astronomer, is being built in Chile. It's got a mirror of 8.3 meters diameter. It's got a camera the size of a small star, and it images into, I think it's 1 billion pixels. And it takes many, many frames each night, and it's looking for things that change in brightness or things that move, transient phenomena. It will identify, the numbers vary, somewhere between 1 million and 10 million such events per night. Dealing with that data flow is going to be interesting. The telescope on the right is the new European EELT. It's also not yet built, but it's coming along, so I think that will be wonderful as well, run by Joint European Consortium. There's many, many new telescopes coming up. Those are just two of them, for example. The next slide, please. Lots of new radio telescopes coming along. The right-hand one, FAST in China, is one of these big bowls in the ground. It looks more or less straight up. It's 500 meters across in diameter. It's the world's biggest single dish radio telescope. But meanwhile, a lot of the world is building the square kilometer array, which is not a single dish, but an amalgam of lots and lots of little dishes. That's got some prototypes that are doing fantastic work, but they haven't really started on the main construction of that yet. It's going to be run out of Jodrell Bank in Cheshire. The next slide, please. This is Ireland's latest edition. This is the Lofar, the Low Frequency Radio Telescope, which has been built at Birr Castle. So this is a lovely aerial view of it, taken from a balloon. That patch that looks like a lot of tiles, you're seeing the covers protecting a lot of much smaller radio telescopes from the weather. And you can't really see very well another array further to the right. It looks like a rather funny array of patches on the ground. Those are our really low frequency antennae there. And the next slide, please. There are space missions. There's the James Webb Telescope, which might launch one day, delayed again by COVID-19. There's Bepi Colombo, which is going to go to Mercury. I think it's doing all right for progress. And the next slide, please. An interesting development is more and more telescopes, like the Vera Rubin, looking for what we call transient effects, stars that flare up, comets that whiz past, asteroids that move, things like that. A number of old telescopes got repurposed for that job a few years back, and they proved highly successful at it. So now the one in the middle on Mount Palomar has had a brand new camera fitted, and it's called the Vicky Palomar Transient Facility. And it's delivering maybe 1,000 new events a night. Again, an issue with how you keep up with this. And the next slide, please. One of these things that transient observing telescopes can look out for is asteroids or other things that might come and hit Earth. If you can get good warning of these things coming and estimate how hazardous they are, you've got some time to do something about it. So I think we'll get better at that as well. And so there'll be less Tunguska events and things like that, less major bits of lumps of rock coming and hitting the Earth and causing a lot of chaos. And the next slide, please. So, sticking my neck out, I suspect that in the next 100 years, we'll have found evidence of life on one of those planets round another star. But I'm not saying it's intelligent life. That dark matter that prevents galaxies and clusters of galaxies from flying apart, finding out what that is will probably happen in the next 100 years, and I think will be a major revolution in our understanding of physics. Equally, dark energy. I'm much less clear what that is, but I think whatever it is, we're going to have to do a major rethink. So that's probably a paradigm shift. And I'm sure that there's many other things that I can't envisage that maybe will eclipse those previous few that I've just mentioned. And the next slide, please. So a photograph, a long-term exposure photograph taken of the Summit of Mauna Kea in Hawaii, showing the telescopes on the summit and one or two cars driving and tracing out the road up. Lovely photograph. Interesting questions about the future of Mauna Kea as an astronomical observatory. It is a holy mountain in the eyes of the native Hawaiians, and they would like it back, please. So we'll see what happens there. Lots to watch. Keep watching, keep interested. I think you'll be very well entertained. And thank you for your interest and your attention.
Well, thank you very much. That was just a truly fascinating lecture, Jocelyn, and it's a pity you can't hear the applause, because I'm sure everybody in their attics and spare rooms and living rooms and kitchens are applauding right now. So I think we're now ready to take a few questions, and if anybody would like to pose some questions, please do enter them into the chat, and then I will pick up on any questions that are coming out as particular themes. So this is going to be really difficult for me because I can already see lots and lots of questions coming in. I just wanted to say, from a personal perspective, some of the things that you've mentioned there when I was an undergraduate were really only dreams that we could imagine. You know, exoplanets, gravitational waves, taking an image of a black hole were just unimaginable, and we've achieved them, and we achieved them with great facilities like the European Southern Observatory, which Ireland became a member of only very recently. And Irish astronomy really has taken a huge leap forward with the building of Lofar and joining ESO, and of course being members of ESA for many years. Okay, so some of those questions have come in. And there's one on gamma ray astronomy that I pick up on here. And the question is, what can we gain from gamma ray astronomy? So Jocelyn, maybe you could answer that.
Gamma rays are right at the high energy end of the spectrum. So you don't expect stars or things to produce a lot of gamma rays because each one packs a huge punch. I think it's a bit like dropping a brick on your foot from about 6 foot high. It's that kind of punch that they pack when they arrive. But they do reveal some very energetic processes. They are an important element of understanding some energetic objects. In fact, absolutely vital. It's just a pity that there aren't too many of them and they're quite hard to detect. But it is a growing branch of astronomy because we recognize that they do deliver a lot of unique information about the energetics, the processes going on.
And of course, UCD have been involved in high energy gamma ray astronomy since its foundation in the 1960s. And Trevor Weeks, who was a UCD graduate, was very much involved in that with the telescope facility in Arizona. A question, that actually a comment was about the name of the Milky Way in Irish. And I thought that was really fascinating, all of the different names. But there's actually two names in Irish. One is Balach na Bó Finne, which is basically a translation. But there's a lovely name called Scríomh Clan Ishnach, which is the writings of the family Ishnach. And the Ishnach family were a kind of almost a mythological family in Ireland. So I think it's a nice story. Okay.
Thank you.
Oh, this one is an important one, Jocelyn. What is the risk of to astronomy from Elon Musk's fleet of satellites? And that comes from somebody you may know, Terry Mosley.
Yes. Risk is huge, particularly for optical astronomers. If you have a real network of satellites up there all glowing, it's really going to complicate observing the sky. It's a right nightmare. And a lot of astronomers are working at the moment to try and at least get it reduced. They may not be able to get rid of it altogether, but it's a huge problem, basically, which we haven't solved yet. I think probably our only hope is, if there are a lot of these bright things up in the sky, if they keep to predictable positions, well, then we'll be able to tell the computer, you know, at that position, and that position, there's a constellation satellite, and ignore it. But it's a huge, huge issue. And I think it's sad from the public point of view as well, because it not only will it muck up the view of the night sky for astronomers, but it will for the ordinary person in the street as well.
Is there anything that can be done by international organizations to legislate to protect the night sky, do you think?
Probably not in time. Astronomers internationally are working with the constellation folk to try and get at least mitigation, and try and get them to understand what the damaging effect would be. So that's about where we are at the moment on that one.
Yeah, and they can also not only produce streaks in optical cameras and optical telescopes, but they can emit radio waves as well, and so they can blind radio telescopes as well. Okay, so let's get into the hard stuff. Dark matter. What is the possibility that dark matter does not actually exist? A question there, Jocelyn.
I think it has to exist. And the way a galaxy rotates is incredibly simple physics, the kind of thing you learn in the last few years of school physics, you know, way before you get to university. And there's no way of explaining the way a galaxy rotates and holds together unless you give it a lot more gravity somehow. And that's basically what the dark matter is there to do, is to provide the gravity to hold the thing together and to allow it to rotate as fast as it does, particularly in its outer regions. It's an amazing conundrum. Vera Rubin, after whom one of those telescopes is named, Vera Rubin was one of the first people to discover that galaxies were rotating so fast, and basically to pose this problem of how on earth they held together. And for a long, long time, people wouldn't believe her data. They'd say, go make more observations, go make more observations, because they just couldn't accept that there was this major problem with how galaxies hold together if they rotate that fast. And the only way we solved it is by this kind of ad hoc addition of dark matter. I think the interesting question is not whether it'll go away, but what the heck it is. What's it actually made of? What kind of stuff is it? Is there new physics in it, or not much? Or so, you know, watch this space.
Yeah, and for any of aspiring young astronomers or physicists out there, if you want to win a Nobel Prize, that's probably the one to go after.
Yes, it's probably your best bet. Yes.
Absolutely. So I'd appreciate a thank you in your Nobel Prize speech for that piece of career advice, please. What else do we have here? Yeah, this is an interesting one, Jocelyn. Teaching and what should we be teaching students about the importance of astronomy to human knowledge, and why it is important to our general knowledge? Why should we be doing astronomy?
Well, I've always found that teaching a bit of astronomy is a good way of teaching physics. People often have a bit of a psychological block about physics, oh, it must be hard, therefore I can't do it, therefore I will assume I can't do it and not really listen or try. And relating it to something like astronomy actually often helps people accept that physics. But yes, yeah, I'm not sure I can say anything else on that.
I mean, I recently was speaking to somebody about measuring the distances to stars. The telescope that we have in Dunsink was built by Grubb, and it was used to measure the distances to stars using parallax. And the question then came, but why do we want to know that? And my response was, because we don't know. But what use is that? Well, my feeling is that all discoveries and all knowledges will have use eventually, but it doesn't also have to have use. We just need to know. That's part of what makes us human.
Yeah. And it would be good to think that we have reasonably complete knowledge, and yet we're being made more and more aware of glaring gaps in our knowledge.
And I like what you said there about young people and astronomy being a gateway into what is perceived as being a difficult subject of physics or mathematics. And they can be daunting, but astronomy is a way into them, and it gives you pathways into, you said chemistry earlier, or biology or astrobiology. So it really is a gateway into many other areas of science, I think.
An interesting chemistry note. We observed some very distant galaxies. We're seeing them as they were millions of years ago. And for example, in these distant galaxies, we can see carbon monoxide. Chemistry was exactly the same back then as it is now, because that carbon dioxide was operating millions of years ago when the radiation set out that we've just received here on Earth. So you can do ancient chemistry by studying astronomy.
I have a question here from a young enthusiast. What can I do to become more active in the field of astronomy?
There may be an amateur astronomical society somewhere near you. But another thing you could do is consider joining some of the citizen science projects. Look on the web, see if you can help with some of the identification, of galaxies like I was talking about. There's quite a few astronomy projects on the web that need a lot of pairs of hands to help analyze all the data. Absolutely, and plenty of online resources at the European Space Agency and ESO as well are worth looking up. There's lots of educational material there. And if I can put in a plug, if you go to lofar.ie, there's also a lot of resources there for kids and young people who may want to learn a bit more about astronomy that we just put up this summer. Okay. Is there a way to protect ourselves from cosmic rays? And if we manage to travel to and colonize Mars, so maybe two parts to that question. Is there a way to protect ourselves from cosmic rays, and what are we going to do on our way to Mars and when we get to Mars? Yeah, and there's an additional hazard traveling to Mars, and that is there might be solar storms, which will give radiations a bit like cosmic rays. Water is quite a good protection, so while you're traveling to Mars, maybe you have the crew cabin inside, surrounded by water tank. Might help mitigate some of the proton events that come from the sun, for example. That's the main cosmic ray thing. Once you've got to whichever planet it is or asteroid you're going to, You're going to need to use the water. You probably can only protect yourself by literally digging in, digging down, going underground, which is pretty hard work. But it's a serious issue, both cosmic rays and solar storms if you're still in the solar system. Sun's been fairly quiet recently, but I'm sure that won't necessarily continue. So I think we've got to remember that the sun can be quite a source of nasty radiation once you're outside the Earth's atmosphere and ionosphere.
And I think we'll probably take one or two more questions. And there's a question here about what inspired you, Jocelyn, to begin this journey that's taken you so far?
As a schoolgirl, I knew I was good at physics, and that was the science that interested me. Chemistry was okay, and biology I really didn't like particularly. And so as I went through my teenage years, I was wondering, what kind of physicist am I going to be in the long run? My father was very, very widely read, and he had an immense general knowledge. And he used to bring home all sorts of interesting books from the public library. And I would check these out each time he brought them home. And on one occasion, he brought home a couple of astronomy books, one of which was Fred Hoyle's Frontiers of Astronomy. And at school in physics, we'd been doing a bit about rotation. And I have borrowed Dad's library book, removed it to my bedroom, and I'm busy working my way through it. And here's Fred Hoyle talking about the rotation of galaxies. And I can immediately see the link with what we're doing in school. And so I thought, right, I'll be an astrophysicist when I grow up. That's what I'm going to be. And then I refined it a bit more to say, well, I don't want to do optical astronomy because I'm not good at staying up at night. There's this new radio astronomy. You can do that daytime. That sounds good. I'll be a radio astronomer. So my schoolmates noted that even before I left school, I knew I wanted to be a radio astronomer. And that's what I did, at least to begin with.
I think we're going to finish on maybe a dream of yours. If there was one question in astrophysics that you could answer, you had all the resources and all the great minds in the world together, what would be that one thing that you just would love to find out about the universe?
To some extent, I've already got that one because I've very, very long been interested in gravitational radiation, which I've not talked about tonight. Is a totally different kind of radiation with its own spectrum. I became interested in this as an undergraduate. In my final year, my tutor was an academic called Ron Drever, who was clearly very, very bright. And I made a mental note as I went off to be a radio astronomer to keep an eye on any field that Ron Drever worked in because it was probably going to go places. And he started working on gravitational radiation fairly soon after that. It's incredibly difficult work. It's taken them about 40 years to develop the equipment to the sensitivity where they can now pick up gravitational waves. I knew they'd do it one day. I wasn't too sure I'd still be around to see it, but it's happened and I've seen it. And I'm watching that field with huge interest. We thought that pulsars would be a prime source of gravitational radiation. We've seen a few pulsars, well, one or two, not many. But they have found that there's a lot of black holes with mass 10, 20, 30 times the mass of the sun. And when those black holes in a binary merge, you get a spectacular shot of gravitational waves, which they can pick up very nicely, thank you. And they're getting now probably a couple of detections a month, that kind of rate, when they're observing. So I'm still watching that field to see what else they turn up, because it's still very early days. But I don't have a specific wish now that they have actually picked up gravitational waves and started studying them.
I think on that ambition, there's a I think we'll draw the meeting to a close, the talk to a close. Thank you so much, Jocelyn, for yet another fascinating talk, an inspiring talk.